The Polygon Clipper is scheduled as being due a week from now. So those of you who haven't finished the first assignment, better get cracking. The Polygon Clipper, if you do it right, will be actually a fairly simple program. You can do it in kind of less than a page of code. The basic idea is that you start out with some list of data items describing the vertices around a polygon. And there'll be x, y, z, w, the homogeneous coordinates of the vertex, already transformed into perspective space, and so forth. And then a bunch of auxiliary numbers, which we don't need to attach an interpretation to right now, but we'll kind of go along for the ride during the clipping process.
See, what do you mean to clip along with? Oh.
Well, we'll get to there in a second here. So the idea is to clip the polygon against the more or less standard 6 clipping planes, which are etc. as described in the write-up. That is, the screen x is -1 and the screen x is +1, top and bottom, so forth. Now, the way that Ed briefly described the polygon clipping algorithm, he talked about taking a polygon and slicing it into 2 polygons, one that's all on one side of the plane and one that's all on another side of the plane. And for the purposes of this, you need to just keep the one that's on the good or the visible side of the plane. So for each plane, you're going to pass the whole polygon through and clip it against that plane, and you'll come up with a result polygon for that. And then you'll take that result polygon and pass it through the next plane, come up with a result of that, and take that and pass it through the third plane, and so forth. Those of you who happen to have read Ivan Southern's article on recursive, or he calls it reentrant polygon clipping, but really the real term should be recursive polygon clipping. He discusses a way of making this algorithm recursive. That is, each stage recurses on itself and calls the next stage. And that's real elaborate and real complicated, and you can kind of understand it, but it's not necessary to clip polygons that way. The advantage of that is that you can clip a polygon with an arbitrary number of edges, because you pass one edge or one vertex at a time down this pipeline, and it comes out the tail end. If you do it the simple way, that is, you clip the whole polygon and come up with a result polygon, you have to have some internal buffer within your program that will hold the result polygon. And so with static storage allocation, you're going to have some maximum number of edges that you will be able to hold in that result polygon buffer. That's okay. Make that something like 20 or 30, and that will keep everybody happy. It's something that you can easily extend if you need to. So you'll take the incoming polygon, which will be a list of vertex elements of this sort, and you'll cycle through each of these things, or each edge, and if a vertex is inside the clipping boundary, just stick it in the result list. If it's outside and the previous one was inside, then you have to compute this intersection here. And compute the intersection which causes where the line intersects the plane. And so you'll come up with a new value for x, y, z, and w interpolated between the x, y, z, and w on each endpoint here. And you interpolate these extra numbers along with it, just as though they were coordinates. So you'll do the same thing to all these numbers in this list. You'll come up with a alpha x1 plus 1 minus alpha x2 goes into the resultant x. Same thing for y, z, w, a1, and a2, and so forth. The alpha, then, is the proportional distance between the 2 endpoints. So you'll clip this polygon and put it in one buffer, and then so you'll have the internal buffer taken, which is the polygon clipped against the first boundary. Then you clip that resultant polygon against the second boundary, and you'll put it in a second buffer. You clip that against the third boundary and put it back in the first buffer. So you're kind of pouring the polygon back and forth between these two buffers, each time shaving off the part that's outside the appropriate clipping boundary. When you come to the very tail end, you're going to have a polygon that's inside the clipping boundary. Either that or else you're going to have a polygon with 0 vertices. If you have 0 vertices, you just return immediately because the polygon is, invisible. It's off the screen someplace. If there's anything left, then you go through and take construct a new list of whatever format is necessary to feed your polygon tiler. And you make that have the values x over w, y over w, z over w, and then the a1 and a2, the same numbers that you started out with here. Now these all might have been interpolated if this particular vertex is a result of the thing going past a clipping boundary, or else they'll be just the intact a1s and a2s and x, y, z's if it was the result of a vertex that was inside the clipping boundary. In any event, you make a list of these up then in whatever format is necessary to pass your polygon tiling routine. And you call a polygon tiling routine. There's only one catch here, and that is converting from canonical screen space into the pixel coordinate space that you want to use. The planes here that I've described, x minus w and x plus w equals 0, that's basically the screen x equals plus 1, screen x equals minus 1, y is plus and minus 1, z, as described in the right, it goes from 0 to plus 1. And so this is a kind of device-independent coordinate system. It's a square screen and a clipping boundary. So that means that at this point here, before you pass the things to your polygon tiler, you have to do another little transformation into pixel space. Basically, you'll probably just multiply the x and the y by 512 to get it so it goes, actually, that's not good enough. X over w and y over w are going to go from minus 1 to plus 1 when they're done. So you're going to have to do something like x over w, 1/2 of that, plus 1/2 times 512, whatever it takes in order to map this into whatever pixel coordinate space you want. Now notice if you make this thing variable, then you can change the resolution of your picture fairly trivially by just changing the constants that you're going to scale the x and y by. All the rest of this stuff up here is in device-independent coordinate space, and it's only just before you go to the polygon tiling routine that you scale it into the pixel space that you want. Okay. That should pretty much do it. You glance over the little write-up and see if there are any further questions on that. Those of you who don't have one, there are more of them around here, various places. A couple of people came in late. It's real nice that the chalk shows up a lot better on the TV set than it does on the live blackboard, doesn't it? Yeah, emits ultraviolet rays or something. Now I want to sort of pick up a little bit where Ed left off last time. We're getting into the problem of drawing pictures of bicubic surface patches, which are the parametric style of defining curved surfaces, as opposed to the algebraic, the quadratic surfaces that we discussed before. Now, he, I understand, briefly went over some of the modeling techniques for defining the shape of these things in terms of geometrically meaningful points, or typically called control points. What you generally have is what looks like a square sheet of rubber, and you kind of pull on these points in different directions, and you can stretch the rubber into different shapes. There are several ways of relating the positions of some control points to the coefficients of the polynomials that you're generating to actually describe the surface. And he mentioned them, but he didn't give you the specific conversion matrices. And so I'm just going to write these down right now so that you can file them away if you need to. You just want to have a cubic interpolant, that is, the curve goes through each of the 4 control points, actually passes through them at the values 0, 1/3, 2/3, and 1 for the parameter. I barely have room on the blackboard here. Okay. That is, you're coming up with a cubic polynomial as a function of t. And if t goes from 0 to 1, the value of x then passes through each of the 3 points in question. Now, there did run out of space here. You have as a column vector the 4 values that you want the thing to interpolate: x at 0, x at 1/3, x at 2/3, and x at 1. So given the 4 values for the control points that you want to interpolate, you just multiply this column vector by this constant matrix. This is scale factor of 1/2 in here, just so I don't have to write 9 halves and 27 halves all throughout the matrix. This will give you a column vector, which are the 4 coefficients of the polynomial: the cubic, squared, linear, and constant coefficient of the polynomial. All of these, all of the different modeling schemes are of this form. There'll just be some constant matrix in here times the column vector of the 4 values of the 4 control points. I'll just write the matrix now of numbers, and it fits in the same way. There's t cubed, t squared, t and 1 kind of coming in here on the left, and the column vector of the 4 control points always on the right. The Bézier form here has the 4 control points. The 2 outside ones are the ends of the curve, and the inside ones are kind of little magnetic force on them that sucks the curve in that direction. So if you move this little point down, the curve will kind of bulge down to try to follow it. I understand Nelson went over some of these things last term, so I don't want to go into great detail on the trade-offs between what's good and bad about the different ones. I'll mention them very briefly. Hope I'm not erasing these things too fast. Hermite interpolant, also known as a Kuhn's patch. Steve Kuhn's was the guy who first kind of came up with this, and so it's named after him. That's if you've got the position at the 2 endpoints and the tangent at the 2 endpoints. P0 and P1 are the locations at the 2 endpoints, and P0 prime and P1 prime are the slope vector, or the derivative, the direction in which you want the thing to be moving. P0 is the value at the endpoint where t equals 0. P1 is the value at the endpoint where t equals 1. P0 is the derivative of the value at p equals 0, etc. This one's good for gluing these things together end to end, where you want to have the things continuous. That is, you want to have the endpoint at the t equals 1 for one curve and the slope at the t equals 1 for one curve be the same as the endpoint for the t equals 0 of the next curve and the slope for t equals 0 of the next curve. So you can make these 2 entries in one curve have the same numbers in them as the other 2 entries in for the next curve along the chain. Yeah.
Doesn't Bézier have the same property?
Bézier has roughly the same property, although you have to flip a sign or 2 in there. You have to make the one that's coming in the same distance up as it is as the other one is down, basically. Well, they have to be collinear. The same distance helps too, but that makes it just a little bit smoother. B-spline. Factor 1/6 out here. This thing takes the 4 control points. P0 and P1 are, again, the value at the thing wants to have at, well, strictly speaking, this is not true for B-splines. Maybe I better just label these a little bit differently. A, B, C, and D. What happens is, if you plot kind of a polygon between points A, B, C, and D, the curve will kind of come near B on one end, come near C on the other end, and it'll be smooth in between. B-splines are also good for gluing things together end to end, because you make A, B, C, and D for one curve segment, feed that in as the 4 numbers. Then the next segment will have an E down here, and so you use B, C, D, and E, those 4 numbers, to make the second curve segment, and it'll go something like that. And then C, D, E, and F for the third curve segment, and so forth. And this makes the joins between these things be continuous in second derivative as well as first derivative.
What are the P's there?
These are, P in this case can be a vector, X, Y, Z, and W, basically. In all these cases, the column vector out here represents the coordinates of a control point. And so this matrix multiplication is kind of a linear combination of all these control points to give you the coefficients of the polynomials that it takes to generate these. Yes. Control points are always the 4 column vectors. And the last one is called the Keval ROM spline, or the Overhauser curve, depending on who you talk to about who invented it.
Which is it on the exam?
Keval ROM. Keval ROM is used sort of in the same way as a B-spline, but it has the same properties as a Bezier curve. And that is, the 2 middle things here are indeed the places where it goes through at t equals 0 and t equals 1. And the PA and the PB are other kind of auxiliary points down here, A and B. And the curve will go through these 2 things, and it'll go sort of in the direction of B on this end, and it'll go sort of in the direction of A on that end. And again, this is good for gluing things together end to end, where you have the 1, 2, 3, 4 thing for the first curve. Then you go 2, 3, 4, 5, feed that in as a column vector for the next curve, and that'll go like that. 3, 4, 5, 6, feed that in, and it'll go through the next curve, and so forth. So that goes through all the points, but it's only continuous in first derivative. B-spline doesn't go through the points, it goes near them, but you don't quite have the control over the point's exact location, but you get second derivative continuity here. Now this is how to define basically just a curve in 3 dimensions. What you'll get out of this then is a set of polynomials t cubed, t squared, t, and 1 are just the basis for the polynomial functions. Each column in here will have a set of 4 coefficients for the cubic, squared, first order, and 0th order term, which generates x. Second column has the 4 coefficients for y. Third column has the 4 coefficients for z. Fourth column has the 4 coefficients for w. So as t varies back and forth between 0 and 1, this set of 4 polynomials will sweep out some curve in space. If you want to define a surface, you need a bivariate function, and that's typically written as this sort of a product here, where you have t cubed, t squared, t and 1 like this, s cubed, s squared, s and 1 is a column vector, and now you have 16 numbers in here, which are the 16 coefficients of kind of all possible combinations of the cube and the square and so forth term. So this is called a bicubic function. One of these 4x4 matrices then contains a coefficient for generating just one of the coordinates, just the x coordinate. So you have another 4x4 matrix, which you can kind of think of as being in a plane behind this thing, which generates the y coordinate, and a third one for the z, and a fourth one for the w. So this is kind of almost a cube of numbers here. It gets hard to draw these three-dimensional matrices as just numbers on the blackboard that way. But each of these things generates a x, y, and a z and a w coordinate. And as t and s vary back and forth, they will spit out values of x and y and z and w, which trace out curves to sweep out the surface. Now these things are very easy to make line drawings of, because you just start plugging in values of t and s and slowly incrementing them, and it'll generate little lists of x, y, z, w points that trace out the curve in space. The trick now, however, is to be able to draw a picture of these things on a shaded image display. It's the scan conversion problem. That is, given a pixel on the screen, we want to know if that pixel lies inside this curve, and if so, what values of t and u, or t and s rather, it corresponds to. That is, for x and y, we have these bicubic polynomials here. And we want to solve those things mutually for x equals constant xs and y equals constant ys. Find all the solutions, there might be several of them, values of s and t which solve this equation. And we know where we are on the patch. Now really, this is even more complicated than that, because if we talk about perspective, the x on the screen is not just a bicubic function like this. It's the x function divided by the w function. So you got this mass divided by this mass, that's x. Similar mass divided by the w mass, and that's y. And so you have to be able to solve that. And that's not generally simple to do, just diving in out of nowhere. The first algorithm that actually did this was one that Ed Catmull came up with, which he started in on last time, which is to kind of go around the problem and do it in a way that's similar to the Warnock algorithm, only in reverse, which is the patch splitting. And that is, you take the patch that you want to draw, and you successively split it into halves or quarters, each of which represents just one of the corners, one of the four corners of the patch. And then you split that into four quarters, and you keep splitting these things down until the little patchlet that you've got here is only 1 pixel in size, at which point you can say, well, let's just call this thing a plane, figure out the normal vector to it at that point, and shade it in. So the trick here is both being able to know how to take one big patch and split it into 4 patches so that each of those 4 pieces will be exactly the same shape as the original one if you just butt the 4 pieces together. And the second problem then is to know, once you've got a patch, is it small enough to draw? Like, is it below a pixel size? And the third problem then is once you've figured out that you want to draw it, what value to use for the surface normal vector. And actually, we need to also figure out something for the hidden surface elimination. Let's take a look at each one of those. How to split the thing in half. Now, there's this big matrix formulation that you can go through and how to do this in terms of the polynomial coefficients. But it turns out that if you deal with this thing as the Bézier control points, which are one of the things that I'd put up here, there's a simple geometric way to describe it. If you imagine these 4 points as the control points for one curve in space, that's like one edge along here, then you can split that into 2 curves by bisecting each of these lines. Let me label these things A, B, C, and D. Start out with the 4 points A, B, C, and D. You split this into 2 and connect this with a line and that with a line. And you split that in 2 and connect that with a line, and you split that in 2. Successive number of halvings of the line. Let me label these things now. A, B, C, small d, and E. So, one I haven't labeled yet. First level splitting does these. Now by A I mean the whole vector here, x, y, z, w, just as a vector. And B is the vector x, y, z, and w. So you take each component of this vector representing point A and point B, add them together, divide by 2, and this gives you the vector for point A. Then you split AC, so you get that B and D equals F plus E over 2, and then small c equals B plus D over 2.
B A plus F over 2.
Which B? Capital B or small b? A plus F over 2, that's right. Thank you. Diagram is a little messy up there, so it's easy to lose a few. A plus F, F plus E, B plus D. Okay, I think we're all set now. Now this tells you how to split one curve in space. This is just the 4 control points of one curve. If you look at a patch, however, you can think of it as a mesh. The Bézier control points for the curved patch is a mesh put together out of the 16 control points, intersections of these things. If you want to split this patch into a left-hand side and a right-hand side, say, you just apply this algorithm to that row of things there, and that'll give you it will give you 7 numbers. You apply the same thing to this row, and that'll give you 7 points. This gives you 7 points, and that gives you 7 points. And now, in this case, then the final patch is A, small a, B, and C. Those are the 4 Bézier control points of the left-hand side of this thing here. And then C, D, E, and then the original big D. Those are the 4 points of the right-hand side of the thing. So this tells you how to split the thing into a left half and a right half. You do the same thing kind of in the other direction if you want to split it in the kind of the front and the back half. That is, you apply the splitting algorithm to these 4 points here, and then to these 4 points, and to these 4 points, and to these 4 points. So what you get out of this thing is if you split it both ways, you get 4 little subpatches, 4 collections each of 16 control points, some of which will be in common. The ones along the seams here will actually have the same numbers in them. So you'll get 4 sets of control points so that if you're to treat each of these subpatches as just a single unit and just butt them up against each other, they'll be exactly the same shape as the original patch. Next, how to tell if it's small. That relies on a property of the Bezier patches. I'm not sure if Nelson went over this last term, but it turns out that you can prove that the entirety of the patch will lie inside of what's called the convex hull of the 16 control points. A little easier way of saying that is, if you draw a box around the maximum, minimum x, maximum, minimum y, and maximum and minimum z of all the 16 control points, the patch has got to be inside that box. All of it's inside. It doesn't have a little thing that squirts out or anything like that. The term convex hull actually means something a little more elaborate than that, but just maximum, minimum, x and y is good enough for our purposes. Is there some...
So in multi-dimensional space is pretty hard to find.
Pardon me?
A convex hull pretty hard to find in multi-dimensional space.
Yeah, probably so. Even in 3-dimensional space, it's no picnic. So as a result, if you just take the maximum, minimum, x and y, that's a little bit bigger than the convex hull, and that's still a good enough approximation to it. Now, strictly speaking, you're really only interested in the x and the y of the convex hull because that's the values that determine whether the thing is on the screen or not. Now, there's a little bit of a problem with this thing in terms of perspective. And that, pardon me, huh?
I'm not sure I see why you need to do it along both directions in the patch splitting. Why you need to do that.
I've just defined how to split the patch into 2 pieces. We're going to put this together into an algorithm in a minute. There's a little bit of a problem with this now in terms of perspective because we want to know if the patch as projected on the screen fits inside the x and y thing. What this thing really does is give us a convex hull kind of in real 3D space. The actual coordinates that you're looking at here are the x, y, z, and w potentially in perspective space. Now the problem with that is that if you take, I want to say that. If you take the control points and you project each of those 16 points into perspective space through a homogeneous perspective transformation and make a patch out of that, you won't get exactly the right patch. You won't get the same patch as you would have if you actually generated all the points along the surface and projected them individually. But it turns out that the difference in this case is not substantial. What Ed did with his algorithm was to make the approximation that the patch is almost the same here. So strictly speaking, you can take each of the 16 control points, project those into perspective space, divide by the W, and that'll give you a screen space value, which tells you if the patch is, how much screen area that the patch fills up. Yeah.
So you're saying is that you're going to get a different looking patch depending upon where you're viewing it from?
Yeah. And if you exaggerate the perspective or not, it'll look slightly different. It won't be
10%, 1%?
Depends on how close you are to it and so forth. It won't be the sort of thing that will be obvious, I don't think, unless you look for a certain specific shape, like a sphere might not be quite spherical or something like that. So we now know how to tell how big the patch is going to be, at least some gross estimate of how big the patch is going to be. So how do we put this into an algorithm? We start out, we examine the patch that somebody hands us. To see if it's bigger than a pixel or smaller than a pixel, just by taking the maximum x and y. Let's assume that it's bigger than a pixel. If the thing is too big to draw, we split it into 4 pieces with this patch splitting algorithm here, and we push all of them onto a stack. And then you go up here and basically you, as somebody whispered in the audience, recurse. You pop the top element off the stack and examine it. And if it's too big, you split it into 4, push those on the stack, and then go back up here. If the thing is small enough to draw, you draw it, and then come back up here to look at the next thing, top thing on the stack. Fairly simple algorithm. When you try to pop the stack and discover that it's empty, this is a really great flowchart, isn't it? It's what happens when you make these things up on the fly. If the stack is empty, then you're done, you return. And then we need to initialize the thing we come in that route. So we start out with the first patch sitting on the stack. Yeah.
Well, what does drawing it consist of when it's smaller than a
that's
pixel?
what we're getting to here now. Guys are impatient, aren't you? What does drawing mean? Good question. We have a patch which is about the size of a pixel. And so there are various details of the algorithm at this point. You want to somehow or other color in the pixel that this thing surrounds with a value of some sort. In order to do that, you need to come up with a normal vector for the patch, and you just plug that into the lighting equation and stick that value into the pixel. We're going to refine this a little bit, but the global outline is figure out some normal vector someplace on this patch and write the value into the pixel if it's visible. Second problem, is it visible? So how do you do normal vectors? Did Nelson tell you how to do normal vectors for bicubic patches? Okay. Mathematics. We have the position of the patch is a vector formed by 3 functions of s and t. So at a particular point on the patch, plug in an s and t, and that will give us a point on the patch. If we take the partial derivative of each of these things with respect to s, whoops, y, and evaluate it at the same s and t value, st, these partial derivatives are still functions of s and t, that's going to give us a little vector that's tangent to the surface in the s parametric direction. If we take the partial derivative of this thing with respect to t, etc., that's going to give us another tangent vector to the surface in the t direction. I'll label these things as p sub s for the point partial with respect to s and point partial with respect to t. These two vectors are tangent to the surface. Their cross product is the normal vector. Partial derivatives of these things are fairly easy to take because they're polynomials, right? To take derivatives of polynomials is real easy. So if you just take the coefficients of the original function, do a little simple juggling around with it, multiply by some constants, 3 for the cubic term and 2 for the squared term and so forth, and plug in the S and T properly, you'll get the equation for the partial derivatives. Okay, we now know how to calculate a normal vector for a desired S and T on here. Now at this point where we want to draw this small microscopic patch, we need an S and T someplace on here. The assumption is, however, this patch is real small. You can use any S and T that you like. You can use S and T both equals a half or both equals 0. It's easy to plug in 0 into these polynomial equations, and they'll be roughly the same. Now we're shoveling a lot of almost the same and pretty close and stuff like that in here, and these do kind of come around to bite you on occasion. If you don't watch out, you get little what looks like wood grain patterns in there where the round off here builds up and then suddenly jumps back and builds up and jumps back. You can start becoming imaginative here as well. You can say, rather than going through all this elaboration of computing these partial derivatives, since we got these things in terms of the Bezier control points, let's take the vector from this corner to that corner and the vector from that corner to that corner. Those are approximately going to be in the plane of the patch. So we'll take the cross product of those two, and that'll be our normal vector. Kind of anything that's in the right ballpark will pretty much work for the first stage algorithm.
What do you do about pixels that overlap separate patches?
Okay, that's the next stage, how to do the hidden surface elimination. If you examine kind of this algorithm and watch it work, this is really amusing to watch it color in, too. It's a good exercise in recursive theory because the thing starts out and it colors in this and then goes around there and then that patch and that patch. And then it does the same whole thing for this and for that and for that. And then does the same whole thing for this and for this and for this, etc. It makes the pixels come up on the screen in a somewhat scattered order, especially if the patch folds over itself and ties itself in a knot. The pixels are going to kind of come up all over the place. This is not a scanline algorithm by any means. And so as a result, you don't really have all the information about all the patches in the same place at the same time for one pixel in order to do the Z depth comparison to see who's in front. So this is one of the things that drove the invention of the Z buffer algorithm. And that is, you keep a giant frame buffer with the intensities in it. You initialize them all to 0 or black, whatever. You keep another auxiliary buffer with Z values in it. You initialize all of them to minus giant number. And each time you come up with a pixel to color in, you compare its Z. Again, what's the Z? Well, pick the Z in the middle or pick the Z in one of the corners, something like that. And you compare that with what's already there. If it's in front, this one wins. You color it in and update the Z value in the buffer. If it's behind, you throw it away. It's already been something else has already been drawn in front of it. Now this particular algorithm is actually fairly simple to implement. And so you can get pictures up on the screen without too much energy. It, of course, has various problems which can be attacked by different, more complicated means, like all this business about approximating the normal vectors. Exactly what does that mean? And things about the order in which the stack is pushed and popped. But those are sort of details. I'll mention a few of them briefly, I guess, but don't want to get involved in it too much. It's the sort of thing that...
What's used in practice, and what is the graph?
What's used in practice?
What is the graph?
Let's see. Trying to think of, I don't know of any places where this is actually being used in a production environment right now. I used, Ed implemented it to get a thesis. I implemented it just to play around with it a little bit. The people at New York Tech implemented it. But it's kind of slow, and it does have all these little problems of raggedness at the edges. In practice, it comes out to being it's the sort of thing that you make a picture and it's crummy, and so you go and look at those particular numbers and see, oh, you know, this can be fixed up by this ingenious kludge, and so.
But people design the patches.
This is just a rendering algorithm. This is not a design algorithm. You design it by you know, various other means. This just draws pictures of it once you've got it designed.
People design patches and then they would run this algorithm to render.
Yeah.
What do people usually use for render? They don't use this.
Well, that's what we're going to get into shortly. This is the first algorithm that came along. And up until this point, anybody who had thought of trying to do this thing looked at the mathematics and said, we got to solve this x of garbage divided by polynomial garbage, and you know, this is hopeless, I don't know how to do it. And
People didn't design patches.
they designed it on line drawing systems. Or else they took the patch and hacked it up into a whole bunch of little teeny polygons. I mean, that always works, right? This is the first algorithm that actually drew a real smooth patch, though, rather than little faceted polygons or mock bands and Garo shading and little lumpies around the silhouette edge. There are some refinements to this thing that you can make, for example, to optimize the order in which the patches are split. Notice here I just said immediately we split the patch into 4 pieces. If it turns out that you have a long, skinny patch like that, you're going to wind up splitting it into 4 pieces, and you're going to have long, skinny little slivers of patch when you get done, which means that you're splitting in one direction more often than you need to. And so one refinement is, instead of splitting into 4, you kind of look at the extent in the 2 parametric directions, and you split in whichever direction makes it come out more squarish, basically. So the first time you'll split it into these 2 pieces, then this one will be split into those 2 pieces, this will be split into these 2 pieces. Now this one will probably be split that way, and then you'll start getting into squarish splittings. Yeah.
If you do make these tiny little slivers, you'll keep going until your longest axis is inside a pixel, right? And
right.
You'll get
It's the longest axis that determines whether you're...
So you'll get a couple inside the same pixel.
That's
so
quite... Yeah, that happens a lot.
What will you
wind
draw?
Up, if you imagine these little points here as the centers of pixels, you can get quite a few of these little patch fragments falling on top of the same pixel. And so the simplest way to do this, you know, you have to start out with some quick and dirty algorithm. So you just, each time you get one that's in there, you just color it in. So it's the last one you happen to stumble across that determines the color here. Now what Ed did when he implemented this thing was to actually go in and take a look at each of these little patch fragments and compute the area that it has. And add that fractional amount of the total area into the pixel value. So he was actually accumulating the sum of the intensities of all these patches, little micro patches, weighted by the area that they covered on the pixel. And this worked pretty well because it averaged out the whole the whole intensity over one pixel to some average value of the whole thing. That tends to be a bit slow, again, because you got to do a lot of bizarre geometric garbage in order to figure out the covered area of this thing. Yeah.
That sounds like it might do a little bit of aliasing for you. If there was 2 different patches of 2 different colors crossing through that pixel, there'd be several different micro patches.
Oh, yeah, right. In general, the Z-buffer type algorithms have the advantage of being simple and fairly quick to implement. And they allow you to do intersections simply, just 2 totally different algorithms can intersect things. But when you look at the precise details of what goes on along the intersection, it's either going to be a pixel from one thing or the other thing, and so the intersection tends to be kind of ragged. Now you can start shoveling more information into the Z-buffer if you want to. You've got the intensity and you've got the depth information in there, and say you can store 1 unit of the edge in here for the last thing that was drawn in. And so when a new thing comes along, it will be compared against that edge to see how much it overlaps what already is there. Then you start talking about having, well, let's have a little list of polygons in here for each pixel. And I'm not a big fan of Z-buffers, to tell you the truth. I think they're simple to get going with, but when they want to do anything real, they start getting bizarre and complicated real fast. Ed Catmull and the New York Tech people are big fans of them because that's their main rendering algorithms depended on that. And they came up with all sorts of ingenious methods of getting around some of the problems. Which, yeah, ingenious methods to get around some of the problems. Well, anyway, patch splitting. What else do we want to get into? Well, we got half an hour. I guess I may as well.
What are you
push it a little bit. I like scanline algorithms myself, where you're breaking the thing down into all the necessary information so that when you're coloring in one pixel, you have everything you need to know about that pixel in the same place at the same time. Either that or the depth sorting type of algorithms, which color in the far things first and the medium things and so forth. They have some problems where things overlap, but they're not quite as severe as with a Z buffer.
But what do you do in a case like this where you curved surfaces?
Well, that's what we want to get into next. So Catmull's algorithm is the first one that drew bicubic patches, and that's kind of got the ball rolling of people thinking about ways of doing it. Now the next thing to examine here is, given that we want to draw patches and scanline type algorithms are, oh sorry, tape change. Later.
Even if the patch lines aren't parallel.
Yeah, you have to be a little bit generous in your assumptions, but you can make it work by more or less straightforward means once you look at the details of it. Okay, scanline patch drawing. The idea here is that rather than do this thing in kind of scattered order all over the screen, we want to scan this thing out top to bottom, left to right, and at each pixel when we get there, we want to be able to know which patches are visible there and which parts of them. We want to be able to find out all the all the S and T values for a particular patch. If the thing folds over on itself, you might see two of it as it pierces itself. And we want to know what's going on at that pixel. And so in order to do that, you need to basically generalize the algorithms for polygons. And so in order to generalize it, let's kind of re-examine the polygon algorithm. Here's a polygon, and here's the current scan line. The current scan line is going kind of top to bottom down the screen. And when the scan line drops below the maximum Y value in this polygon, it's added to some active polygon list. So we've got a list of all the polygons that intersect the current scan line. And as the thing scans down the polygon, once it's in the list, each time you go down one Y value, you're going to update all this little information about the edges, where the edge intersects the scan line. Now, since it's a straight line, you can just add some delta increment in X for each scan line you're going down, another delta increment in X for each scan line you're going down here. So you do that while the polygon covers the scan line, and then when the polygon or the scan line goes below the polygon, it's now no longer intersecting us, and so you can remove this from the active polygon list. Then the inner loop to this thing, the X loop, is going through for a particular scan line. It's going across the scan line, and when the beam more or less intersects the left-hand edge of the polygon, it's added to kind of an internal X visible list. As you scan across this thing, when it goes to the right, it exits the X visible list. Again, internal to this thing, you're updating things like the Z and the intensity information as you scan across. So we want to come up with an analog of this thing for patches. Well, suppose we have a patch that looks something like this. It's basically some shape in 3D. It doesn't necessarily have straight edges, and it does not necessarily be planar. It might bulge out a little bit or something, but it's the same sort of thing. As the polygon, or as the scan line passes down there, when it passes what amounts to a local maximum on a patch, it has to be added to the list. And as long as it's visible on there, it stays on the list, and you're updating values. When it passes the local minimum, it has to be removed from the list.
So the only difference is you can't do it from computational
Well, you do what amounts to incremental computations, but in a different way. You can't do incremental computations by just adding constant values because these edges, say, are not going to move in a linear fashion. Similarly, when you go across one scan line, when you hit the left edge of the thing, you have to include it in this internal x-active list here. And as you go across, you're recalculating the z value, say, as you go across. And when you pop out the right-hand side, you remove it from the x-active list. So we need to find out what extra sorts of mathematics we have to do in order to do all this maximum and minimum and intersecting sort of calculations. First thing to notice is that when you have a polygon here, the intersection for the outer loop of the scan line, which is basically you take a plane from the eye through the scan line, defined by the point at the eye and the line at the scan line, that makes a plane in space, and that's going to intersect all the polygons. And so that's going to give you a whole bunch of little straight line segments if you look down at it from the top. If you do that to a bunch of patches, however, they're not necessarily going to be straight line segments. They're going to be curves, and they might actually be circles and funny things like that. So you can't represent these things just as their endpoints, or just as linear equations. And in fact, these curves in 3D space, or in what's now a 2D space, we're kind of looking at top view here, so we have the x and the z-axis like this. This is the intersection of the curves with one scan plane. The way these things are defined is by saying that the function that defines the y of the patch is equal to a constant value, y scan line. Now actually this y function in the perspective case is the ratio of y, the perspective y, and the perspective w. So this is potentially kind of a bizarre function here. Once you have taken that, though, you can sort of plot it. Here's the s-axis, and here's the t-axis. And this will make some sort of bizarre thing like that. The place where that intersects the y scan line here is going to be some constant y contour of this thing. So all the points S and T that you can plug into this thing that will give you this y scan plane, those are all points which generate points that are on this intersection curve. So if you plug all those points into the x over w function and the z over w function, they will trace out this curve in 3 space. So this curve here is defined kind of indirectly in a two-step manner. First you find all the s's and t's which solve the y equals constant problem, and then you plug all those s's and t's into the x and the z functions, and that'll give you the curve. This is basically not a nice function to play with. It's not something that you can just write down a few coefficients and that describe this curve. But basically all is not lost. You can represent that curve by, even though you can't represent the whole thing, you can just make a list of, say, its endpoints, and that'll give us a good first approximation of the curve. And we can generate the rest of the curve later on when we want to. We just need these seed points. The seed points are caused by, for example, the intersection of the edges of the patch with the current scan line. It's the same thing as the edges of a polygon with the current scan line. And so what we're going to do is keep a list of these things as values of s and t instead of values of x and z explicitly. Now, it turns out that there's a lot of extra special cases involved in patches beyond what you wind up with in polygons. And they come in 2 different types. First of all is local maxima. With a polygon, the local maxima, the thing that triggers the thing to be entered into the active list, is just one of the vertices is just bigger than all the others. And so it's easy to find the local maximum of a polygon. You just look for all the y's and the maximum one. Now in a patch, you can have a local maximum like that, same sort of thing. One of the corners of a patch is bigger than everything else. And so that's one type of local maximum. You can also have a local maximum which falls in the middle of the patch like that. Since the edges of these things are no longer straight lines, they can bulge out, and so that's the point that triggers where the patch should start showing up on the screen. Or you could have something in the middle of the patch. It could be a bump like that. And so that point triggers where the thing shows up on the screen. So basically what you have to do first, before you do anything else, is find a list of all the local maxima on this patch so that you know where to trigger that the things are going to enter in. And you can do that, basically there are various numerical methods for doing that. It's called nonlinear optimization theory or something like that. It's some function of two or more variables. You want to find out the values of those things that gives you the maximum payoff, basically. Now, once you've found a local maximum, then the first scan line that this thing is visible for, you want to add a new segment to your active list, and you're going to represent that by the coordinates at the two endpoints here. Now, in the case of a corner patch, let's do this thing in parametric space here. The two endpoints are going to be just kind of down from the edges a little bit like that. And as the scan line moves down one step at a time, you need to update the S value and the T value at the two corners to go from one patch, from one scan line to the next. Let's take a quick peek at how you might do that. How are we going to trace this edge as the scan line goes down the screen? What we've got here is along this edge, it's just got it's a one-parameter function because the S value is equal to 0, right? And so we want to find out for a given Y scan line what the value of T is that will cause this thing to be equal. Now, you can't necessarily solve this Y function directly for T because this thing might be something bizarre, bicubic over a cubic. But you can do it numerically. One simple way of doing that thing is Newton iteration. Newton iteration basically starts out approximating this function by a linear function. We begin by setting coming up with a function. We want to find the zeros of this, basically. We just subtract off the Y screen. And so it's going to look something like that. And you start out with an initial guess at that. And the way the Newton iteration works is that you fit a straight line to this guess by taking the value of it and the slope at that point and putting a straight line through it and extrapolating down back to the 0 axis like that, and that's your new guess. And then you evaluate what the function really is at that point. It should be closer to 0 than it was before. And you find out what it really is and what its slope really is, and you make that the new guess, and so forth. So basically the loop looks something like let me make sure I don't get this botched up. Right. At each step in the iteration, the new value of t is equal to t minus f of t over the f prime of t. This is the derivative with respect to t. And again, this thing might be bizarre, but you should at least be able to calculate derivatives of it. If it's a polynomial or a rational polynomial, you can still calculate derivatives of it. You start having to do derivative of this polynomial minus this over the square of the bottom and junk like that, chain rule for derivative of the ratio of two things. But you can do it. So at each y step, then, you go through this iteration until you come up with a value of f of t that is the y value, which is real small. That is within a tenth of a pixel unit, something like that. And so the first guess that you use when the thing enters is the value at the corner. Then you Newton iterate on that until you converge to the value here. On the next scan line, you Newton iterate on that, starting with this as the initial guess, until you get down here. And on the next scan line, you iterate on that, starting with this as the initial guess, until you get down there. So the whole thing is numerically tracking along the edge of this thing. You can't just use a difference equation by adding some delta x and delta z in here. You have to do a little bit more work in order to track along the edge. Let's look at the second type of local maximum entering edge. Here's what the thing looks like on the screen. And here's the place where it first shows up. And so the local maximum winds up being in the middle of the edge. And if you imagine this intersection here projected back into the parametric space, it's going to make some little, say, parabolic shape here like that. So that means that the first guess that you might pick is where the local maximum is itself. But that's not going to work too well because since it's a local maximum, you're going to wind up dividing by the derivative, which is 0 at a local maximum. And so you have to do something a little bit more elaborate, which I won't go into details of, but you have to look at the second derivatives of this thing in order to approximate the curve locally, and that'll give you your initial guesses. And then once you've got those, then again, each scan line down, you do the same sort of iterative scheme on that. You do a Newton iteration to go one step down, Newton iteration to go another step down, and so forth. And so you're tracking along the edges as they go out like that. Third type of local maximum introduces another interesting problem. Here's what the thing looks like on the screen. Here's what the thing looks like in parametric space. Just as we go below this local maximum, it's in the middle of the patch, right? And so here's the local maximum, and the first scan line down from that is going to be some little circle around that. This doesn't hit the edges anywhere, right? As a matter of fact, you look at this thing, and where this intersects, it doesn't hit the edges anywhere. So we're not going to have any little edge thing to track along. But we are going to have something else interesting. We're going to have the silhouette edge here to track along. That's the second type of edge that you want to keep track of when you are iterating down on this thing from one scan line to the next. You want to know where the edges intersect the scan line, and you want to know where the silhouette edge outline intersects the scan line. Because that'll tell you the extent of the patch in x and y. That's the value that you have to iterate in between. So the silhouette outline is defined by Zn equals 0. Now, again, you can say Zn is equal to I don't want to go into all the detail, but you know the z component of the normal vector is comes from the cross product of the s and the t derivatives. The zn component of that thing is going to be something like xs yt minus xt ys, where these subscripts represent partial derivative with respect to s, partial derivative with respect to t, partial with respect to x, partial with respect to t. Again, in perspective, each of these things is the ratio of x over w, and so forth. So this is some god-awful mass equals 0, some huge monstrous polynomial in s and t. And you want to also find the place where y of s and t equals 0, which is going to be some other polynomial of s's and t's here. So you've got this enormous mess here, which defines some curve in ST space. It's an algebraic curve, as a matter of fact. And this enormous mess, which defines some other curve in S and T space. This is the curve that the silhouette line is going to track. And you have to find the intersection of these two. That is, you want to find an S and T value which satisfies both these equations. So you have to do what's called bivariate Newton iteration. We used to have just one function of variable equals 0. Now we got two functions of two variables equals 0. We want to find the solution to both of those. If we were to plot these two functions, we're going to get some surface like that for the Zn and some other surface for the y. Now where the y thing intersects the 0 axis, it's going to make some curve. Where the z thing intersects the 0 axis, it's going to make some other curve. And basically what bivariate Newton iteration does is you start out with a point, and it locally approximates the y function with a plane. Given the value of the point and the s and the t derivatives at that point, it'll put a plane through that. And that plane will intersect the 0 axis on a line. And it'll take the z function, and it will approximate that with a plane, given the z and the u and the v derivative of that. And that will intersect the 0 plane at another line. Where these two lines cross, that's the next guess that the bivariate Newton iteration uses. Now, in mathematical terms, that's some god-awful mess. I'll write this down. This is the last big, nasty equation I'll get into. This is a hunk out of the giant $35 book, and so if you're all turned on by this, you can go and spend $35. It's a reprint of an article on that I wrote, which is an excerpt out of my thesis, actually. Scanline algorithm for displaying parametrically defined surfaces. So it's in the big Kelly Booth compendium of stuff. The general form of this solving two things, you got two functions, f and g, and you want to find the value of u and v where these are both 0. I switched variables on you. Sometimes these are called s and t, sometimes they're called u and v. Keeps the mind supple. Basically, you wind up with something similar to what we did for the single variable Newton iteration. It's the old value minus some function over some bunch of derivatives. In this case, it's the value of f times partial respect of v of g minus partial respect of v of f times value of g divided by partial of f respect to u times partial of g respect to v minus f respect to u, g respect to v. Each of these things is a function in its own right, bivariate polynomial, which you can evaluate at the current guess, at the current value for u. There's a similar expression here for v, which I won't write down. It's just the same thing in there with the u's and v's reversed. And this will give you the next guess at the function. And so as you're tracking down the screen, then you'll be able to keep track of the s and t values, or u and v values, depending on how you want to name the axes here, as this thing crawls down the screen for each successive scan line. And as was pointed out, what you do is, for the initial guess of this thing, you use the value that you had at the previous scan line. Okay, it's rolling on towards 5 o'clock, so why don't we pause at this point.
How slow is that?
It's